The entire planet is warming up. Earth's average temperature has shot up over the last 150 years, and we've measured it everywhere. But what's causing this? Why is the temperature rising at this precise moment? For decades, scientists have been extremely cautious about this issue. Why? Well, if you look at temperature data, the first thing you'll notice is that this rise coincides with the moment when human beings began burning coal and oil and natural gas on an absolutely massive scale to provide energy for our civilization. And guess what's also been rising during this time? When you burn organic matter, its carbon atoms bond with the oxygen in the air to form carbon dioxide. So we can hardly be surprised when we measure the amount in the atmosphere and find that it's gone from 280 dioxide molecules per million to over 400 in just 150 years. The conclusion? It's obvious. If carbon dioxide and temperature are both rising, then we're clearly to blame for global warming, right? Actually, that's not necessarily true. Just because two factors change in the same way, it doesn't mean they're related. For example, here are the number of divorces in Maine versus per capita margarine consumption. And here is the average age of Miss America compared to the number of people murdered by hot objects. If both show the same trend, does that mean one caused the other? Nope, it's just a coincidence. So, how can we tell if these two graphs are related or not? Well, first of all, coincidences usually don't last long. If we expand the time frame, we find that these graphs no longer line up. And as we'll see in an upcoming video, when scientists study how temperature and carbon dioxide levels have evolved over hundreds of thousands of years, they find that the two tend to stick together. During ice ages, they both dropped, and in interglacial periods, they rose. In addition, this isn't like margarine and divorces. There's a clear mechanism that connects these two quantities. When sunlight reaches the Earth, two things happen. Part of the light bounces back and returns to space, and the rest is absorbed. The Earth heats up and sends infrared radiation into outer space. When that infrared radiation tries to pass through the atmosphere, carbon dioxide is waiting to nab it. The thing is, carbon dioxide and other compounds are molecular machines designed to let sunlight through and simultaneously trap the infrared radiation emitted by the Earth. While other molecules like nitrogen are completely unaffected, carbon dioxide absorbs it and starts vibrating. All the energy that light was carrying, all the heat that was going to escape into outer space, now it's stuck here with us, and it's making the Earth's temperature rise. This is the famous greenhouse effect. And don't assume it's a bad thing. Without it, our planet would be a huge ball of ice, and we probably wouldn't even be here. But it also follows that if the amount of greenhouse gases gets too big, the world will become a car in an outdoor parking lot on a sweltering summer day. So it's no surprise that, since carbon dioxide has increased, the temperature is also rising. However, we need to be careful. There's no denying that this graph has some strange oscillations. Of course, the Earth is a terribly complex system, and the greenhouse effect is just one of many factors that can alter global temperature. So, why don't we take a look at them? Maybe it's caused by something else. First, we have solar activity. The sun is the source of practically all our energy. If it gives off a little more or a little less light, that has consequences for our climate. There are natural alterations in the light that our star emits. For starters, the energy we receive from the sun varies slightly in 11-year cycles, which we can measure directly using our satellites. Now, these changes are so tiny and so fast that our climate doesn't react to them. Because the water in our oceans is resistant to temperature change, it acts as a buffer against these variations. It's like putting a pot of water on the stove and quickly turning the knob on and off again. The water won't be affected by it at all. But maybe the sun has even longer cycles that we haven't been able to detect based on just 50 years of measurements. This means that scientists have to figure out past solar activity by indirect means. One is the sunspot catalog, which is over 300 years old. More sunspots equals more solar activity. But another, more ingenious method involves using tree rings. You see, there are ultra-high energy particles that come to Earth from deep space and crash into our atmosphere, cosmic rays. Very occasionally, one of those particles, specifically a neutron, collides with a nitrogen atom and turns it into an unstable carbon-14 atom. This new carbon-14, randomly generated in the atmosphere, is gradually absorbed by plants via photosynthesis, which weave it into their tissues, for instance, a tree trunk. The funny thing is that at times of high solar activity, the sun bombards us with its own particle streams that deflect these cosmic rays, and since few of them can enter the atmosphere, less carbon-14 is formed. So by measuring the amount of carbon-14 a tree has in a certain ring and making some adjustments to compensate for its instability, you can know what solar activity was like that particular year. If the concentration is very low, it means there were major solar storms that prevented the formation of that carbon. If it's high, the opposite is true. This allows us to chart solar activity over the last 10,000 years. And yes, those data do reveal bigger oscillations. The most important for us is the one that happens every 200 years and is presumably the culprit of certain colder periods in history, or little ice ages. Well, according to the sun, guess who should be in one of these little ice ages right now? Have you noticed the temperature dropping? Because I haven't. This not only rules out the sun as the cause of global warming, but it also tells us that we're now entering a period of minimal solar activity, which will partially mitigate the effects of climate change. Imagine what'll happen when the sun stops working in our favor. Since we know it's not the sun, another important factor is the Earth's movement around the sun. Of course, there's the classic revolution and tilted axis that gives us summer and winter every year, but there are other movements. The Earth's axis changes its angle of tilt and precesses. Plus, the ellipse of our orbit elongates and contracts, becoming more or less eccentric. The results of these variations in our orbit are called Milankovitch cycles, and they're very important in climate history. The ice ages of the last 1 million years have been determined by eccentricity, and the amount of ice during each one depends on the other two movements. Could they explain or be contributing to our current climate change? No, for two reasons. The first is that these movements are incredibly slow. They take tens of thousands of years to complete. There's no way that such a sudden change in temperature in the space of just 100 years could have been caused by such sluggish movements. The second reason is this. At no point in the last million years did any of these periodic movements bring the level of carbon dioxide above 300 parts per million. I'll say it again, periodic. This climate change we're experiencing is something entirely different. Okay, since it's nothing external, perhaps the problem is on Earth itself. But are we sure it's us? After all, plants and volcanoes also emit carbon dioxide into the atmosphere. Plus, we know these natural eruptions have caused climate changes in the past. How can we be certain that all those greenhouse gases are our responsibility? The answer lies in carbon. We've already talked about one of its isotopes, carbon-14, but there are two others, carbon-13 and carbon-12, the most abundant of all. Every carbon has a different weight, which means that during photosynthesis, plants and some bacteria tend to capture more dioxide with carbon-12 than with carbon-13. This carbon is absorbed, like before, into the tissues of the plant or bacteria, and after a time it's released as carbon dioxide. In other words, when scientists measured the concentrations of different carbons in the air and found that the proportion of carbon-12 to carbon-13 had increased as carbon dioxide levels rose, they were able to deduce that the source preferred carbon-12 over carbon-13. The source was living things. If it were a volcano or even the ocean, there would be no difference between the two carbons, which means we can rule them out as the main culprits. So, if carbon comes from living things, could it all be chalked up to forest fires, deforestation, or the decline of plants for other reasons? Well, they may contribute a small amount, but the bulk comes from somewhere else. How do we know this? The key, once again, is in the carbons. As I said before, carbon-14 is unstable. It's like a little ticking time bomb. It falls apart after a certain amount of time. In our bodies, the same thing happens as happens in tree rings. We have molecules made of carbon-14. When these particles decay, new carbon-14 atoms enter our bodies via the food we eat to replace them. But when we die and stop replenishing the supply, the proportion of carbon-14 gradually diminishes over time, decaying at a steady rate. This missing carbon-14 is exactly what paleontologists use to date ancient corpses. However, the carbon-14 dating technique isn't just useful on bones. It can also be applied to the air itself. And it turns out that the carbon dioxide entering the atmosphere doesn't contain carbon-14, which means it must come from living things that died hundreds of thousands of years ago, trapped underground until all their carbon-14 decayed and returned to the surface to, I don't know, fill a motorcycle gas tank? Folks, I'd love to tell you otherwise, but all the arrows point directly to us. We've got the crime scene, the motive, and all of the witnesses are against us. It goes without saying, some of you will continue to deny it. You'll distrust some or all of the points made in this video. I've put some books and articles in the description if you want to check the data. And you'll decide to blame some other natural process that scientists, those idiots who don't have a clue, have overlooked. I'll leave you with some food for thought. We can do one of two things: either take our role in climate change seriously and do something about it, or shrug it off and do nothing. If climate change ends up having a major impact and we're prepared to face it, we can prevent and lessen quite a few of its consequences. If we're not, it could completely eradicate our way of life. On the other hand, in the unlikely event that time passes and nothing happens to affect us too drastically, that the Earth even cools back down and this becomes La La Land, then if we haven't taken measures, well, the world will keep on turning. We'll go on exploiting, wasting, and consuming as we do now until we run up against another problem to deny, like the shortage of fresh water. But if we do take those measures, at least we'll have developed the necessary technology to switch to renewable, efficient, less pollutant energy sources. If I were a person living in the year 2100, I don't think I'd be cursing our families for having made this last decision. After all, the world's supply of oil isn't infinite, so we're just getting a head start on a transition which, at some point, will need to be made anyways. However, if climate change turns out to be as awful as it seems, I guarantee you that what they think of us in the future is going to be anything but pretty. So that leaves me with one last question. If you had to make the decision right now to do something or not, would you take the risk? And remember, if you want more science, just hit the subscribe button.